What's everybody? What's up, everybody? So let's do some problems with concentration. Just a quick reminder: I've got a few problems for you. 1, 2, and then there's a third problem. Okay, kind of looking at just the basic overviews and how to do some calculations. You do it with these particular compounds. You can do it with any compound. The only thing that changes is the compound formula, and so then the mass numbers and that type of stuff. So let's just jump into this. So all right, we got 2.5 liters of solution and 60 grams of sodium chloride. What will be the concentration of the solution? Pretty elementary type problem. First, let's list everything that we know we have. So the volume is the 2.50 liters. Great. We've got 60 grams of sodium chloride. That's mass. So that is 60.00. So we got 4 sig figs here. Grams of sodium chloride. So we write NaCl. And so what will the concentration? Concentration we know is molarity. So there's capital M will be our concentration. Okay, so we remember from our studies, right, that molarity, all right, and you can just look this up on your reference sheet if you can't remember it. Molarity is moles of solute per, okay, liters of solution. And I guess I should write MOLE. If we're writing it in the equation, I should write MOLE because MOL is the actual way you write the unit for mole. So I should write mole with MOLE. All right. So molarity, that's what we're solving for. So here is basically our X, right? Liters of solution, that's the volume. So we've got this. Moles of solute, we're given mass. So we cannot directly plug this into this equation because we're given what we need in mass units, but we need this in mole units. So obviously, here's where we're just going to take molar mass, right? So you're going to bring this down, grams of sodium chloride for every 1 mole of sodium chloride, and that would give us our mole. Using the molar mass, that would give us how many moles we have with a 60 gram sample, right? So if we go back to our periodic table. Remember sodium 22.99 because we're going to use 2 sig figs. And then chlorine we see over here 35.45. That 3 is not going to round it up, right? So those are going to be the numbers that we will use to figure all this out, right? So we're going to come back over here. We've got 22. Oh, see, got to turn it on first. 22.99 plus 35.45. You should come up with 58.44. Right? So right here we know that this is 58. Wow, that's pretty messy. Let me try that again. 58.44. It's a little bit better. Alright, so now we just 60 divided by 58.44. We see that is 1.02669, and that would be moles NaCl. 60.00 is 4 sig figs, so let's see, 1, 2, 3, 4. 6 and 9, we can see that 69 is probably going to round that up right there, so we should see 1.027 mole NaCl. Okay, and then there's more numbers after that. There's like a 4045. I believe you should get that. Double check my math, but I'm pretty sure that's right. So now what we have to do is we basically have to do some basic algebra 1, really, right? So we want molarity, and there's our equation right there. So now that we have moles, we know that we have 1.027 moles of sodium chloride. That's per volume, and our volume is 2.50 liters of solution, right? And so we take the 1.027 divided by 2.5. You get 0.4108. Let me do that again just to double check. 1.027 divided by 2.5. Yep. So we get 0. Got to add the placeholder. We say point this, but you got to add the placeholder. 0.4108, and then remember moles per liter. Moles per liter is molarity, and then you just bring the sodium chloride unit over in a Cl. And you see here that we've got 4 sig figs in this answer. And let's see, so there's 4 sig figs here. 60.00, that's 4. 2.50, that's 3. So remember, the rules are when you multiply and divide, the final answer you want to have the least sig figs possible of your original measured values. Well, in this case, 3 is less than 4. So first, second, third significant digit. That 8 would round that up, and so a good final answer for this one would be 0.411 molar NaCl. Okay, put a box around our final answer. This one's good to go. All right, pretty straightforward. Not too much to that one. All right, so let's see what we got here. Let's drop down. Let's go to something a little bit different here. We've got. All right, in lab you find 700 milliliters. That's going to tell us volume. So volume equals 700 milliliters of potassium chloride. How much salt was used to make the, of a 0.5 molar, right? So we've got molarity. So it's 0.500 molar, right? We've got molarity. So now we just need to kind of figure out how much salt was used, right? So how much salt was used? So it wants the mass of salt. That's what it's asking, how much was used. Because your scales measure in mass units. They don't measure in moles, right? That's a calculation. That's a fundamental calculation that we have to do, right? So come over here. So let's see, let's go back to our basic equation. Molarity equals moles of solute per liters of solution. Molarity right there, check, we got it. Moles of solute, that's what we're trying to figure out, is moles of solute. So we don't have moles up here, so the first thing we realize, we'll have to do some dimensional analysis, some converting of units here in a little while. And then we've got right here 700 milliliters. This says liters of solution. So it should already be ingrained in your mind, in your thinking, that you always have to have this in liters. So when you see 700 milliliters, the first thing you should be thinking about is how many liters is that? And for some people, I know that this might be a little bit of a struggle in your mind. Hopefully it's not, but if it is, remember, we're just going to look at some strategies. We need to basically just convert milliliters to liters, because we want to put milliliters on the bottom, right? And we know that basically there's 1,000 milliliters for every 1 liter. So if you divide it by 1,000, it would just take this decimal here and move it 1, 2, 3 places to the left. So we know that would be 0.700 liters. Okay. Now we have everything we need to solve this problem here, just about, right? So, we're trying to solve for mass of salt, which is going to be somewhere in this. So molarity, check, we got that. Liters, check, we got that. This equation right now is currently set up to solve for molarity. We need it to solve for moles. So if you were in math class, basic math is you would need to isolate this variable by itself. So obviously we're going to multiply this side by liters of solution, so it cancels out here, which means we'd also multiply this side by the liters of solution, correct? And so the new form of the problem would be moles of solute equals molarity times liters of solution. Our molarity we know is the what, 0.500 molar, right? 0.5 molar, and we know that that is the potassium chloride, so that would be KCl, right? And then we're going to multiply that by liters of solution, which we've got 0.700 liters of solution. Let's bring this problem up here a little bit for us to look at. I tell you what, probably going to need some more room. Let me take this, and I'll bring this down so we have more room. We'll be doing that problem here in a little bit. We don't need that right now. Okay. So, right here, now we look at this. It's easy to take those numbers, punch them in a calculator. But if you look, you'll notice that when we're done, this is solving for moles. But we don't have moles anywhere. We have molarity and we have solutions, but the mole unit is anywhere. We have to get that on the screen. So remember, we can just go backwards. If we can go moles per liter to get molarity, we can take molarity and go backwards, all right, and derive it back out. So that's 0.500 moles of potassium chloride per every 1 liter of solution times 0.700 liters of solution. You should see that liters on top and bottom, that unit cancels out. It's all about the units. It's always about the units. Always, always, always about the units. So now, at this point right here, you should see 5 times 7 is 35. If you struggle with moving decimals, just sort of in your mind's eye, just use a calculator. So 0.5 times 0.7, you should see that you get 35 in there, but you have 0.5, one number after a decimal, 0.7, another one, that's 2, so it just makes it moves 35 to 0.35, right? So that's 0.35 moles of potassium chloride. We don't want moles, we want right here, what we want is the mass. What do we need? Molar mass. So now all you do is take this and 1 mole of potassium chloride, we just have to figure out what's the molar mass, right? So we go back to here, we see potassium 39 right there, right? We see 39.098. This 8 is going to round that up, 39.10, right? That's what we will use, 39.10. And remember, we had already said over here 35.45 for chlorine, correct? All right. So let's go back over here. Let me double check this. So potassium, we said, yeah, 39.10, right? So we've got 39.10, 39.1, the calculator is the same thing, right? Plus the 35.45. You should get, right here, you should get 74.55 grams of potassium chloride. So this is the molar mass, right? And I always like to double check my numbers. Of course, I don't always do that, and sometimes I make mistakes. Okay, I make mistakes a lot. 39.1 plus 35.45, 74.55. All right, so units. Whoa! Sorry about that. Right? There we go. Black or blue, same thing. All right. So that is gone. So now we just have the 74.55 times 0.35. You should see that now we've got 26.0925, and then the only unit that is not canceled out is grams of potassium chloride. So now we just have to evaluate this answer down to the correct number of sig figs, right? Alright, well, let's see here. Let's go back to our original measured values. We had, I'm sorry, well, 3 molar, right? And typically we think of that as like the 3.0 at a minimum, right? Oh, I'm sorry. Wrong problem. I'm up here still on problem 2. Pardon me. So the 700 milliliters, 0.700, 3 sig figs. 0.500 molar, again 3 sig figs. So everything we started with was 3 sig figs. So let's report our final answer in 3 sig figs, right? So there's 1, 2, 3. There's a very strong argument that 9 is going to round that 0 up to a 1, right? So final answer, 26.1 grams of potassium chloride. Pretty easy. All right, one more. Let's take a look. 3 molar potassium chloride. So that gives us molarity. Is needed if 41.83 grams of salt is needed for the reaction. So that gives us mass. So that gives us mass of potassium chloride equals 41.83 grams of potassium chloride. How much of the solution? So how much of this is going to be needed? That if you got a solution that's in liquid form, we need volume. We need to know how much to actually pour out of the container, right? So the volume. This is what we're solving for, is the volume. How much of this? So how many liters, how many milliliters do we need to actually pour out? And so we can evaluate this down here once we calculate the numbers to figure out what's the best way to report this, right? But the standard way is always report it in liters. All right, so let's go back to what we know. Let's see, we've got molarity. Let me move this up a little bit. So we've got molarity equals mole of solute per liters of solution, right? So we need to solve for volume. So we can already see that before we do any kind of work here, that we would have to rearrange this equation so that instead of solving for molarity, we're solving for liters of solution, right? Solving for liters. So you would obviously multiply this side by liters of solution. It would cancel out here. Check, it's gone. But it's an equation, you got to do it to the other side, right? So obviously you have to multiply this side by liters of solution as well, right? And so now what you have is liters of solution times molarity equals moles of solute. So now I'm going through these steps because I realize that there are people, there's a lot of you that you can see this in your head, in your mind's eye. You can look at an equation, you can move variables x, y, z, a, b, c. You can move things back and forth. You can see it in your mind's eye. But I've been doing this long enough to know that there are enough students out there that they need to actually see the step-by-step process. So that's the reason I'm doing this right here. Okay. So again, we're trying to solve for volume. Means we need to get the volume part independent. We need to get it by itself. So obviously now on this side we would have to divide this side by molarity, so it cancels out, which means you have to also divide this side by molarity. So the new form of your equation, right, would be liters of solution equals moles of solute per concentration, the molarity of the solution. Okay. So so down here we see we need molarity. We got molarity up here. Check. Liters of solution. That's what we're solving for right here. That's what we're solving for. We can't put a check on that yet. So now the question also is we got mass of salt, but we need moles of the salt, right? So obviously, going to have to go to molar mass and convert it from grams to moles. All right. So potassium chloride, we already up here figured out that 74.55 grams per 1 mole. So we can just use that, right? 74.55 grams of potassium chloride for every 1 mole of this substance. That unit crosses out. Right? So now we've got, let's see, 41.83 divided by 74.55. Let me double check my math again. 41.83 divided by 74.55. All right, if we've all done this correctly, we have 0.56109999, and this is like 33, right? So 33. So we know that that equals the moles. Oh, I'm sorry. Moles of potassium chloride. So we had 4 sig figs here, right? 41.83. So let's go, let's see, 1, 2, 3, 4. That 9 is significantly high enough to where we can do one of two things. We can take this 9 and round this up to a 1. Or we could actually leave this 9 here and use extra digits in the calculation. Either way, you're going to find out that the answer pretty much is going to be the exact same when we're done. We really won't have that much of an effect on it. If you're in a lab where precision is highly important, and usually what happens at that point is you're using scales that are calibrated out at least 4, 5, 6 digits out there because you just need that much precision for accurate results, right? So for here, we can just use 0. Looks like a 6. Try to fix that. 0.561 1. Why not? Moles of potassium chloride. All right. So now this is the new form right here of our equation, right? So moles, we've got 0.5611 moles. So 0.5611 moles of potassium chloride divided by the molarity, right? So the molarity is 3 molar. So we've got 3, and typically you always put a decimal of at least 1 decimal place when you write your number so that it is as precise as possible. 3 molar, right? You got a 3 molar solution. So at this point, it's pretty easy to do this part right here, right? And it's potassium chloride we're working with, right? So you could actually write 3 molar potassium chloride, right? All right. So now let's do something real quick. Let's just do the numbers. We'll get to the rest of this in a second. 0.56. Hey everybody. Pause for a second. So if you just finished doing that calculation, you realize Tib just made a mistake. So if you redo it, I think in the video I said 0.56. So I said, so take 0.56 and divide it by 3. And yes, you see that we get that 0.1866666. But I forgot to put the 2 ones. So I would have lost points on this. I would have messed up seriously bad. I would have had some results that would have been a little off. I would have had some error in there. But you should see that if you divide out 0.5611 by 3, you'll get 0.187033333. So the final answer should be 0.1870. So the rest of the video, it's all sound. I just forgot to put in the 2 ones, which is very important. Don't forget to put in your ones. Don't forget to put in all your numbers. Remember, check your work. I'm notorious for not doing that. Divided by 3 gives us 0.186666, and it keeps going, right? So we got 0.18666, and that gives us plenty of numbers on what we need, right? So let's go back up to here. We see we have 41.83 and 3 molar. The best answer on this is going to probably be 4 sig figs, since 1 sig fig or 2 sig figs from the molarity is not going to be enough to really give us a good indication of how much volume we're pouring out. So we're going to want to go with the 4 sig figs, right? So we look at this right here, and in the calculator we've got 0.18666. So 1, 2, 3, 4. We could really stop right there if we wanted to. We don't have to write the rest of that stuff. We just need one number to help us evaluate this, right? And then of course, now this is going to give us 0.1867. There's our 4 sig figs. Now, liters of solution is what we're solving for. So when we're done, we need to have liters of solution. So you should be able to take a look at this and see that those 2 units, they're gone. See, if you, it's all about the units. If you carry your units with you along the way, you'll never go wrong. All right, you'll never go wrong. So now we've got to look at this, and we realize we've got moles and molarity. Don't see liters anywhere, right? But it's in there. It's in there. So let's drop down here. Let's give ourselves a little bit of room to work with here. All right. Many of you will be able to see this in your mind's eye, but there are people who they need to see this. So let's take a look at this. Let's go back to some very basic pre-algebra. If you've got moles per molarity, right? So what that means is you got moles per, and we know molarity is, right? We know molarity is moles per liter. We know this. So what this means is we've got moles, this is divided by moles per liter. Now, we were taught a long time ago, even before you did algebra, when you were doing just basic fractions, when you're dividing out a fraction by another fraction, when you're dividing out something by a fraction, that you have to end up multiplying by the reciprocal. So that means we would have moles times the reciprocal, which would be liters per mole. And you should see that immediately, right there, moles is gone. It's gone. It's gone. We're left with just what we need. This has worked out perfectly. We're left with liters. So right here, the only unit left, when we divide all of that, we divide those 2 numbers to get this. When we divide all these units, notice that goes away. We're just left with liters. That's how many liters we need. That's it. We're done. That is it. So you should be able to see that, right? Let me move this. And we'll just move this out of the way for us for a second. So you should be able to see that, let's see, we needed 4 sig figs. Well, there's our 4 sig figs. So we need 0.1867 liters. So this is the correct answer. This is the correct answer. Okay? This is the correct answer. There we go. So, but in lab, to get 0.1867 liters, you probably measure out a certain number of milliliters. So this right here is the final answer. So in a real time, as you're practicing though, you ask yourself, well, what would I actually pour out? Well, if we have 0.1867 liters, for those of you who have trouble doing this in your mind's eye, I'm showing you how to do it. And with enough practice, you'll be able to do this without having to actually write it down. So we know there's 1,000 milliliters per 1 liter. Liters cancels out. We're left with milliliters. If you multiply this by 1,000, it's going to move the decimal over 1, 2, 3 places. So in lab, you would pour out 186.7 milliliters. That's what you would pour out. And that's a skill that you already have. So this is pretty easy. So there's the final answer. This is what you would report on a quiz or a test if you were to talk about it. In practical sense, you know to convert this to this unit here, so you can actually pour that, measure it out. And that's it. There's 3 basic problems for molarity. Something if you're calculating volume, something if you calculate mass, and then right here, and then another problem if you just want to figure out, what the actual concentration of something is. So we just took all 3 variables, kind of did some stuff with it, right? Hope that helped. I'll see you soon. Bye. Good luck.